Hi, we are going to start chapter 3, and chapter 3 will feel a lot like math because the first section of it, in fact the majority of it, will be learning about vectors. You've heard me talk about vectors in chapter 2, saying that displacement, velocity, acceleration, these are vectors. But now you learn a little more about how vector math works. And although it's similar to your normal math, there are some special things that you will learn about, and that's important. Okay, and then once we have mastered vectors, we will move on to two-dimensional motion. So you saw in the last chapter that we studied one-dimensional motion, which was either just along the x direction horizontally or along the y direction vertically, right? So we studied free fall in particular. And now we'll combine two motions. So an object could both be translating horizontally as well as vertically. For example, if you're moving from this point here to there, you're changing your vertical displacement. You're going higher up in height. You're also moving to the left along the x-axis, the horizontal axis. So we'll look at these kind of motions after we have learned vectors, okay? So let's look at section 3.1, vectors and their properties. I mentioned in chapter 1 or 2 that we have two types of physical quantities. One is a vector, the other is a scalar. A scalar is just a number. It has no direction associated with it. For example, the mass of a person or the temperature in the room, this would be a scalar quantity. So it can have a unit, for example, 77 degrees Fahrenheit, yeah? But it won't have a direction. A vector quantity, on the other hand, has both magnitude, which means a number or the size of the object, and a direction. So a scalar is completely specified by just one number, and the vector is specified by a number and a direction, okay? So in the one-dimensional motion, we saw that that vector could be positive or negative, and that was sufficient to tell us the direction, because you're either going to the right of the origin or you're going to the left of the origin. But when we move to 2 dimensions, we'll find that just having positive or negative is not sufficient. Okay, you then need to have positive or negative in 2 directions, either the x and y, both being positive or negative. Okay, so you need to specify the positive and negativity of both directions. Okay, a little bit about how vectors are written. So vector notation in a book, you'll often find the vector as a bolded letter, okay, with an arrow above it is possible. Even if it doesn't have an arrow but is bolded, it will be a vector quantity. Okay, if it has an arrow above it, it's definitely a vector quantity. So if you're handwriting, like if I write on the board or something, I'll put an arrow above it. And when you see the same letter represented with an italicized A, which is not bold, then we're just talking about the magnitude of this vector. That means how large or small the number is, which is associated with that vector. Okay, so here we are not talking about its direction, just the magnitude or the size. So here we have 2-dimensional space. Remember what I taught you about looking at graphs. Here's the origin. This is my x-axis in space. This is my y direction in space. Okay. And what we have here are 4 orange arrows, and these are effectively 4 vectors, which are actually basically the same vector. They're all exactly the same. If I pick one up, I can place it on top of the other. So all of them have the same direction, so that without rotating the vector, I can place it on top of the other ones. Okay? They're all parallel to each other. At the same time, they have exactly the same size. So that means the magnitude is the same. So the length of the vector is determined by the size of the magnitude of the vector quantity. The larger the magnitude, the larger the vector. Here we find that all of them have the same length. Therefore, we can pick one up and put it anywhere. And this is one of the first properties we see about vector space. So this space is called vector space. And we find that a vector which is parallel to itself and of the same size is the same vector. Okay? So 2 equal vectors have the same size and are parallel to each other. Okay, now we want to learn how to add vectors. You'll soon see that this will get very important as you go on doing physics. So say you have two displacements, one after the other, a displacement A and then a displacement B. Your object starts at the start of displacement A. Where is its final position? What's that final vector? So that's going to be the sum of vector A and vector B. That's the total displacement that has been made. And the resultant vector is this vector R. So this is a vector addition. Okay, that's why all these quantities are bolded. They even have arrows above them. Okay, so we want to know how to add two vectors. Since the vectors have magnitude and direction, this is non-trivial. If their direction is exactly the same, it's parallel to each other, then you can just add the magnitudes and you keep the direction the same, and that's your resultant vector. But mostly the vectors that we need to have will not have the same direction. They will not be parallel to each other, in which case we need to resolve them and figure out what the resultant vector is. So there's two ways of doing that. There's the geometric method, okay, this one, and there's the algebraic method. So we're going to see each of these, and we will ultimately use the algebraic method a lot more than the geometric, but you do need to know how to do the geometric because it informs some of your algebraic method. Okay, so let's look at the geometric method. First, you're going to make your coordinate systems. You're going to make your x and y axes and put an origin. And as soon as you make that, you need a scale for your graph. That means if your vector is 20 units long, are you going to have 20 units along a certain direction, be those 20 units? Or are you going to have 5 units represent the 20 units? Or are you going to have 4 units represent those 20 units? So those are different scales, yeah? Or you're going to just have 2 units, in which case 10:1 is your scale, okay? Then you're going to draw your first vector to the right length, okay? Vector A in the given direction specified, say 30 degrees north of east. Then you're going to draw that, okay, of a length maybe 5 units. And then you're going to take the next vector and you're going to draw it on top of the arrow of the first one, okay? So the arrow of the first one effectively is the origin, if you like, for the second one. And then your resultant is going to be from your initial starting point to the final arrow. So let's look at this. This we call tip to tail method. So here's my first vector, vector A. At the tip of this, I have placed vector B. Remember, vector B may not normally be here. Vector B may have been anywhere else, but I can pick it up in vector space and place it over here. It's the same vector B. It needs to just be parallel to how it was before. Yeah? So you can't change its direction. You can move it parallel to itself. Okay, so if I want to add A plus B, then I go from my initial starting point to that final ending point, and this vector R pointing in this direction towards the final, from initial to final, is going to be my resultant vector R, graphically. So this is your resultant vector from the tail to the tip. Okay, so the tip of the arrow is called the tip. And if you measure out its length using a ruler, that's going to give you the magnitude. You have to multiply by your scale factor, don't forget that. Yeah? And the units will be the same as the units for vector A and vector B. Both these vectors, A and B, have to be in the same units. Let's say in centimeters, or both have to be meters per second of their velocity. So they have to have the same units in order to be added together. Okay? And you can measure the direction by measuring the angle with respect to the x-axis. So that's how you do the geometric method. If you have more than 2 vectors to be added, so let's say you have 3 vectors, A, B, and C, you can then continue this process, okay? So we'll see that in a minute. Now we learned how to add vectors A and B, and due to the commutative law of addition, which applies to vectors, this means it doesn't matter whether you add vector B to A or you add vector A to B. So the order doesn't matter. So this is what we did before, vector A, and on its tip we have vector B, that's my resultant. And the next time we start with vector B, so here we start with this vector B, we're now going to place at its tip vector A, so I'm going to pick this vector up and put it here. And my resultant now is from this initial point to that final point. So this is the resultant. This is B plus A. And look at these two resultant vectors. Can I pick one up and put it here without changing its direction or magnitude? Yes, indeed I can. So they are the same vector. Yeah. So here's the process of adding more than two vectors. Here's my vector A, B. The next one, if I want to add C, I place it at the tip of B. If I want to add another one, D, I place it at the tip here. Remember, it always needs to be picked up and put parallel to itself. And you can keep doing this for however many vectors you have. When you reach your last one, let's say here we have A, B, C, and D. D is my last one, then I need to have my resultant going from the initial starting point to the final ending point. So this is my resultant here. R, vector R equals sum of vectors A, B, C, and D. And if I measure this length, it's going to be the magnitude of vector R. If I measure the angle with respect to the horizontal, I'm going to get its direction. Okay. So let's look at a problem. Laura walks 25 meters in a direction 49 degrees north of east. Then she walks 23 meters heading 15 degrees north of east. Finally, she turns and walks 32 meters in a direction 68 degrees south of east. What is her final position? So how are you going to start? You read the problem. It might be a good idea to draw your north, south, east, and west. Huh? So here's the drawing of north, south, east, and west. North is always upwards on the paper, and then that determines where east and west are, and of course where south is. Okay, so it's good to draw this little compass so that you have it with you. So she first walks 25 meters in a direction 49 degrees north of east. So here is east. We're going to make that our x direction. Okay, so I'm going to translate from here to my coordinate frame, where I'm going to say she starts at the origin. So I'm going to put my origin right where Laura is, and she starts walking. This direction is east, this is north, and everything else is set. So she starts off at an angle 49 degrees north, so I need to go 49 degrees north of east. Yeah. And how far does she go along this direction? So this is the direction, this is the line. She goes 25 meters. So I've chosen this as my scale. So 1, 2, 3, 4, 5 units. Yeah. So each unit of this represents 5 meters. So this is 25 meters north of east. That purple vector is my first vector for how she walks. Then I need my second vector. Then she walks 23 meters heading 15 degrees north of east. So I now need 15 degrees north of east. Obviously, it's going to be a shallower slope than this one. And this time, she walks 23 meters. So it's going to be slightly shorter than this one. Okay, so you're going to draw it accurately and measure out 23 meters on your scale. And then you're going to draw the third one. Finally, she turns and walks 32 meters in a direction 68 degrees south of east. So here's my east. I need to go south this time. I'm measuring from here 68 degrees. And along this direction, we need to go to 32. Okay, so sorry, 32 units. Now I need her final position, which means I need to add vector A and vector B and vector C. So I'm going to take on my lowest diagram here, I'm going to bring them all down. I'm going to start with vector A. At the tip of it, I'm going to bring down vector B parallel to itself. At the tip of which I'm going to place vector C parallel to itself. And then I'm going to get my resultant from the starting initial position to the final position. So this is my resultant R. I can measure the angle with respect to the X. So it's 7 degrees south of east. Yeah. And she ends up 50 meters away. So the magnitude is 50 meters. Okay.